Okay, so here we're going to prove Philip Hall's theorem. G is solvable if and only if every non-trivial CLP subgroup has a complement. There are two lemmas we will focus on first. I will use the numbering from the book. The first one is lemma 9. Neither of these lemmas use representation theory. They both just use the theory of solvability. So we can prove them. If G is solvable, and the order of G is bigger than 1, then there exists a normal subgroup such that P is a P group. For some prime P. The cheating proof. So it's stated as an exercise in 6.1, but now that this proof is much, much later in the book, it cheats and gives you the answer, or an answer. And the answer is to recall that a group is solvable if and only if it has a derived series that's finite. Got to remember which way the derived series goes. Remember, if you're solvable, your derived series is finite. And the n minus first derived subgroup is actually abelian. Why? Because we also showed that this was a normal series whose pairwise quotients were abelian groups. So the fact that this is the trivial group means that this pairwise quotient is isomorphic to this group. So G to the n minus first derivative is abelian. Just let P be any CLO subgroup. Of G to the n minus 1. Then because it's abelian, it follows that P is characteristic. In this group, this derived subgroup. And what do you have? You have P is characteristic in a subgroup that is normal in a bigger group. You might remember that implies that P is normal in G. So what do we have? We have a normal subgroup that is a P group. Where is this condition used? Well, we need it in order to have this derived series be long enough that this thing is a non-empty group. Note, there's a reason we say that this is a P group and we're not claiming it's a CLO subgroup of G. And the reason why that is because the way this proof worked, we took a CLO subgroup of a subgroup of G. There's no guarantee that it's a CLO subgroup of the larger group. And so this proof only allows us to get a P group. It doesn't allow us to get anything else about it. But it turns out that's enough to accomplish our aims. So, nice proof. Uses a bunch of different facts from the course. Shows the power of using characteristic subgroups and concepts of being abelian and the derived series. The next lemma basically tells us something that has nothing to do with solvable groups, but it tells us what happens if you've got things that look subgroups that almost have complementary orders. So suppose you have factored your group as a product of prime powers, and suppose you have two subgroups with the following property. For all I, either pi to the ai divides the order of h, or pi to the ai divides the order of k. Note this is a mathematical or, so it's possible that it divides both. Then congratulations, h and k are what are called supplementary subgroups, which means you have this feature. But it does not mean that their intersection is the trivial subgroup. Instead, it turns out the only thing we can say is that their intersection has size given by the GCD. And so this takes into account the fact that sometimes you could have both cases happening. So if a prime divides both, then that prime power corresponds to elements in the intersection. That's what this part of the lemma is saying. So if this case never happens, then you actually do have h and k are complementary subgroups, which is something that will pop up when we actually prove the theorem. But it turns out we need this more general lemma because there's steps in the proof where you want or and you don't want exclusive or, and then you just argue later that you end up in the case where this GCD is exactly 1, and then you declare victory anyways. Alright, the proof of this lemma is not too bad. I mean, suppose pi ai divides h. Take hk. Remember, this is the set of little h times little k. H runs over h, and k runs over k. You can certainly write this as the disjoint union over all k and k. Write cosets hk, right. Let me make my cursive k so it's clear that that's lowercase. Note each of these has the same size because they're cosets. They each have size capital H. So pi to the ai divides each of these cosets. So it divides the whole set. The same thing is true if I put k here instead. Instead, I'd be working with left cosets of k instead of right cosets of h. The same argument works. And so no matter what, the prime powers of the primes with the right exponents divide this set. And so I can say it divides this set for all I. Then the order of g, which is the product of all these primes, powers. Since these prime powers are distinct and they each divide hk, by Euclid's lemma, this product also has to divide hk. Oh, but remember hk was a subset of g, so this size has to be less than or equal to g. So the order of g is less than or equal to this size of h times k, which is less than or equal to g. What does this mean? It means that these two sets have the same size. Since h times k is a subset of g, we now see that they're actually the same set by size considerations. Likewise, from earlier in the book, h times k had size order of h times order of k divided by the order of their intersection. Since we now know that this h times k also has order g, which is this product of primes, we see that the difference between the numerator and here is that the numerator might have higher powers, and the only higher powers it has corresponds to primes that appear in exactly both, which would be things that are in the intersection, or would have to be in the intersection. And so this forces the size of the intersection to have to be the GCD. Because the only way for this equality to be true is that once you multiply and clear denominators, oh, I see, it switched to pencil. You get this product of HK divided by the product of the PI, or the order of G. And so the only thing that's left over are the powers of primes that have to appear in exactly both. And that would be exactly the GCD. Alright, a third fact we're actually going to need for our version of the proof for one of the directions is the Schur-Zasenhaus theorem itself, which I actually haven't stated yet, so I'll state it now. So it states let H be a normal subgroup of G, and H is a Hall subgroup. Which means that the order of H and the index of H and G are relatively prime. Then H has a complement in G. So I've mentioned before that the textbook proves this theorem under the name of Schur's theorem in chapter 17 using a lot of group cohomology tricks. And so it reduces to a certain case where H is abelian, and then that result relies on group cohomology, and we'll give a attempt at a self-contained proof that avoids that part. And it's worth pointing out, if you look at exercise 33 in section 6.1, it refers to another exercise in the same section, and those two exercises alone give you an alternative way to prove the forward direction of Hall's theorem that avoids the Schur-Zasenhaus theorem. So it's worth pointing out, even though I'm going to use this theorem, it's not necessary for the proof. There are proofs that avoid it entirely. However, it's quicker this way, so I'm going to use it. And it's a good excuse to introduce this theorem. Anyhow. And so we're going to use this theorem. And so now we have our pieces assembled. We can prove our version of Philip Hall's theorem, which in our case is an if and only if. So the forward direction in our case is we're going to assume G is solvable. And we're going to let P divide the order of G. And we want to claim that the CeLO P subgroup of G has a complement. I should, of course, state that it turns out that you can prove an even stronger result. Not only are there complements, but all the complementary subgroups that exist are all conjugates of each other. So that generalization of CeLO, I'll state that later in a different video, because this is already complicated enough. There's also a version of the Schur-Zasenhaus theorem that involves conjugacy, but that proof is so hard it actually relies on the classification of finite simple groups to be complete. All right then, so we proceed by induction on G. On the order of G. And by lemma 9, there is a normal subgroup in G. That's a P is a Q group. Well, there are three cases. The first case, Q is not P. Then we can pass to the quotient and look at G mod n. Notice that G mod n has order of G divided by the order of n. Since the order of n is a power of Q, this quotient group is divisible by P. And if you let P prime be Pn mod n, you definitely have P prime has the same size as P. It's still CELA P subgroup. And by induction hypothesis, P prime has a complement. And G mod n. This would be a group we'll call K. What is the order of K? Well, it's a complement to P prime, so it has to be order G divided by P to the n, where n is the highest power of P that divides G. So I guess to make life easier, let's say the order of G is P to the n times m, where m and P are coprime. Oh, sorry, this shouldn't be G. This should be times whatever the order of n is. So K has order m divided by n. Using the isomorphism theorems, this means there exists a K prime subgroup of G with K prime divided by n being K. So K prime has order m. Congratulations, you found a group whose order is complementary to P to the n. So P has a complementary subgroup. Based on order considerations, their intersection is the identity. And based on order considerations, this set product has to be the whole group. And so P has a complementary subgroup. Well, what do you do if Q is equal to P? Well, let's suppose for a moment that this order of n is less than P. In other words, that n itself is not P. It's the CELA P subgroup we were starting with. Well then, what do? Well, we do the exact same trick. We pass to G mod n. I'm going to let P prime be Pn mod n, and apply induction again. We get K is complementary to P prime, which means K has a certain order. Here we have to be careful. It's the order of G. Now I'll have to, again, the idea is then there exists a K prime, such that K prime modulo N is equal to K. The difference here is that K prime modulo N is actually equal to M, or the order of G divided by a certain power of P. P to the N. Something like that. Or not K prime. You don't actually get a complementary subgroup. You still have a power of P's remaining. Why? Because this N is still in here, and the order of N is a power of P. And you have to take that into account. However, K prime is a subgroup of G, so K prime is solvable. And N is the CeLO P subgroup in K prime. So again, you apply the induction hypothesis. K prime has a CeLO P complement. We'll call it H, which means H has order of M. H is a subgroup of K prime, which is a subgroup of G. Look, G now has a subgroup of order M. So P has a complement as well. At long last, we're in the last case. The order of N is equal to P to the N. Well, then this means that P is a normal subgroup of G, so you can apply the Schur-Zassenhaus theorem. The more direct proof would be to apply a Frattini argument, or to apply lemma 9 to the quotient to get another prime power subgroup for a different prime that's normal in the quotient, and to go through a bunch of finagling, and it takes a lot more work. So it's a lot quicker to just cite the bigger theorem that uses a lot of the same proof techniques anyways. So no matter what case we're in, you can find a complement to your CeLO P subgroup. So we see now that whenever G is a solvable group and P is any CeLO P subgroup, it must have a complement. Now we prove the reverse direction. I will state that the proof in the textbook actually leaves steps to exercises from a previous chapter way back in chapter 3. So I'll save that for a different video to finish the proof, and I'll include those exercises or the special cases we need as lemmas before I finish the proof. So, yep, it turns out the textbook uses 2 lemmas for this proof, but it turns out we're already needing at least 4.